right. So we're going to be sharing with you how to actually build hands-on a generative AI agent. And so what we've done today is that we decided to show you our journey in building our own generative AI agent for our Astra Assistant. And I'll be going over some of the lessons learned and how to do it. And then Alex is going to be helping us dive right into the code and showing you exactly where you need to code things up to build your own. All right, so I'm going to first give you an overview of the assistant, what we're trying to do. Then I'm going to talk a little bit about architecture, how the generative AI workflow and the various components needed. Then I'm going to go step by step on how to build a retrieval-augmented generation workflow. We'll talk about the data pre-processing that's needed, how to generate highly contextual prompts, and how to execute the prompts and what to do afterwards. To give you some context to what we're doing at DataStax is that we're using generative AI to improve the results of our self-service business. So when customers use our website and they want to use our app, we've already used AI to increase our subscription business by 5x. So now what we're doing with generative AI, which is different from predictive AI, is reduce the time it takes for people to actually deploy their apps in production. And so today, because databases are very complicated pieces of software, most of the time we use actual real agents, real people to help them out. And this is our journey in replacing those people or augmenting those people with generative AI agents. So our key metric to get to production, our key metric that we care about is shortened time to production. Because the typical thing that happens for a software service like ours is that once they start using the software and they finish their first use case, then they tend to spend more money for their second use case. And we get them through this cycle through this, a lot of times people just use the chat app to help them get through this cycle. So our Astra Assistant that we built, it's primarily focused on answering some of the technical questions. It leverages our chat history and the documentation, etc., to answer these questions. And we also use it as a mechanism to tell people about how much it costs, as well as get help. And there's also the ability within it to refer or escalate to an actual person. So we don't have 24/7 support for our this chatbot. So we're primarily thinking about using it, especially during the off hours. All right, with that, I'm going to hand it over to Alex, who's going to show you a demo of how it works.
Awesome. Thank you very much, Alan. Cool. So what you're seeing here is the dashboard of our product, Astra. If you haven't created an account, you can create a free account at astra.datastax.com/register. And on the bottom right of the screen, you'll see this chat icon. So this chat icon for the past couple of years has been managed by a team of support engineers. And just recently, it's now powered by the assistant Alan just mentioned. So I'm first going to start by asking a simple query. How do I generate a token? And I'm going to add this no context text. And what no context does is it tells the assistant that we don't want to inject any additional information in the prompt. And you'll see, because we haven't injected any additional information in the prompt, we get an answer from the bot that has nothing to do with DataStax, Astra, or Cassandra. So here you can see we get some information on how to generate an API token from Google documentation. It has nothing to do with Astra. This is super unhelpful for our users. So now I'm going to ask that same question with information from our documentation and on our users in the prompt. And you'll see with the improved prompt, we get an answer that's super relevant to Astra. So here you can see exactly how to generate a token. Some of this information was pulled directly from the docs. And later in this session, we'll teach you exactly how to do this, the importance of prompt engineering, and how you could potentially build your own bot like this. We can also ask more advanced questions like, tell me about my databases. And because in the prompt, we also include information on the user, all their activity, we get this super awesome answer back on exactly the databases the user has created. And we can also ask the bot to generate sample code. So here you can see we have the bot generated just a simple sample app on exactly how you connect to Astra using Python. And I'll hand it back over to Alan to talk through exactly how you can build this on your own.
All right, thank you. So there was a lot of magic behind the scene that was going on. So stick around and we'll be able to show you that magic. Before we get started to get to that magic, let's talk a little bit about the workflow you need to build these, what we call retrieval-augmented generation workflows. These are retrieval-augmented generation basically means pairing up the large language model with your data set. And by putting the two together, you generate these highly relevant prompts that allow the LLM to give you good responses like what you just saw. So at a high level, the first thing you need to do is you want to define what your agent does. Is it a chatbot? Is it an enterprise search application? Is it a GitHub Copilot? You want to do some definition of what it actually is doing. Then you want to provide, you want to select which LLM you use. Then you want to figure out what is the data that you're going to be using to augment the large language model with. And then figure out how to take that data and properly put it into what we call vectors. These allow for the LLM to semantically figure out what is relevant information for it to process and build that prompt. Then we leverage that information to build the prompt, and you code it up. And then we have to figure out how, when we actually launch it in production, how are you going to maintain this generative AI agent, and how you're going to do it, how you're going to deal with your operations. So with that, there's a lot of various different tools, and there's a lot of different decisions that you have to ask yourself when going through all these decisions. So this is kind of the architectural work that you need to do up front. All right, let's take a look at the overall architecture. So at a very high level, what we showed you is an application, which was the chat application. It's talking to your agent. This is the agent that you code up. In our case, we coded up in Python. And it's leveraged a combination of proprietary data. This is proprietary structured data, just like any kind of data you'd store in Cassandra today. And then it also leverages proprietary unstructured data. This is the data that's retrieved via vector search. And this is a brand new capability that we've added to Astra DB/Cassandra very recently. Now, in order to deal with your unstructured data, you need to leverage something what we call an embeddings API. So this embeddings API takes unstructured data and turns them into the vectors that's needed so you can do the semantic search. And we'll get into more details on it later. And then last but not least, when the agent is being executing, it calls these data sources and the LLM in order to return it to the application. Now, there's a lot of different technologies you could use. And so today, what we're going to demonstrate is obviously leveraging DataStax technology. For proprietary structured data, we're leveraging Astra DB. For our vector data, we're also leveraging Astra DB, leveraging the new vector database capabilities. The embedding APIs, there's a lot of different technologies you could use. There's technologies from Vertex AI, that's from Google, OpenAI, SageMaker, Hugging Faces, etc. There's a lot of different embedding models today. And then today for LLMs, there's also a lot of various different applications available today. OpenAI, Google Cloud, Google Vertex AI, Hugging Faces, etc. And we want to make sure that when we're doing this execution, we want to actually have it execute in one of the clouds because latency becomes very, very important. We want to make sure that all these services are running in one cloud in a secure location. So the technology that we're using underneath the hood for this one is the LLMs from Google. we're using the vector database that we have. We're leveraging the embeddings API from Google Vertex AI. We're leveraging LangChain. And then we've also open sourced a new project called Cas.io, which basically allows you to create these highly scalable agent memory, which plugs into all the very common frameworks, such as LangChain, and hopefully very soon, Llama Index. So why don't I go into talk a little bit about the first step, the data preprocessing. So I wanted to give you a little context of what vector search is. So vector search is a way that you can interact with unstructured data. And the reason why this is so important is because the LLMs need to have context, needs to have information, proprietary information, especially unstructured information, in order to generate very relevant responses. These can be information from your chat's history system, from actual people conversations. This can be documentation, this can be policy information, etc. And the reason why this is so important is because if the LLM doesn't have context, if it doesn't have information, then a lot of times that's the reason why it actually creates a lot of hallucinations. So let's talk a little bit about how embeddings work. So the first thing is that what you would do is that you would map your database items into an embedding space. So we're leveraging an off-the-shelf model, a neural network to generate these embeddings. And you can see for every single piece of data, it's mapping into this space. Now, at the time of inference, when you're actually doing the vector simulated search, what it does is that when somebody types in a question, it figures out what are the documents that are near it. So in this case, in this scenario, what it's doing is that it's mapping different pieces of text to this embedding space. And then somebody's asking a question, what is like a good Shakespeare tragedy? And it finds out the very nearest neighbors, like Romeo, Juliet, etc. So for our use case, we have two sources of unstructured data that we care about. One is our product documentation. This tells people how to use the product. This is probably the primary source of it. And the second is chat history. And what the chat history does is that it gives the AI agent example questions and answers that people ask. And this is important for not necessarily for finding the answer, but especially in the scenario, because that information is in the product documentation, but it gives kind of an example. This is also what we call few-shot learning of how to answer these questions. So we take this information, we generate embeddings, and then we write the embeddings and the raw text directly into the database. So what does the raw text look like? So for example, this information here is right from our documentation. And it generates about 1,500 vectors, sorry, 1,500 scalar values to create a vector. And this is the data that allows you to do a similarity search. So with that, I'm going to hand it over to Alex to show a little bit about how the pre-processing works.
Yeah, let me share my screen again. So what you're looking at here is a Colab notebook where we demonstrate how you can potentially, process all your data like Alan just mentioned. So I'm just going to walk through all the cells and how you could potentially build an app to do this. So at the top, really basic setup, right? We install all our necessary dependencies. Like Alan said, we're using Vertex AI for this demo, right? So we need to install Google dependencies along with the Python driver, our own Python driver that supports vectors. We do some basic environment variable setup, right? We need the intercom API, we need Cassandra creds, we need Vertex AI creds, and then the process is pretty straightforward. So first, what we do is we call the intercom API to pull all our conversation history. So this is just kind of a simple call to intercom to get all the conversations and then iterate through each of the pages of conversations. Down here, we do some Google Vertex AI setup. We load the library, we set our project ID, we load our credentials. And it really is just a couple API calls to create the embeddings. right? So here we can see, here's just kind of an example of how you create embeddings. Google has a very simple get embeddings API where you can feed in the raw unstructured text and you get back an embedding. So if you wanted to kind of create embeddings for all of the intercom conversations, it's pretty straightforward, right? So here we're doing some basic setup of the tables in the vector store, right? We're creating the chat table, we're creating an SAI index, and then all we do is we iterate through a list of conversations. For each conversation, we generate the embedding, and then we're loading it all into Cassandra. So pretty straightforward. And down here, we just have kind of an example of how you potentially make a vector search once you've loaded all this data. So in order to actually query the vector store, you would need to convert your search query into an embedding, right? We're doing that right here. So let's say the question is, where do I find a token? We'd first generate the embedding. And then it's a really simple query, right? Get the raw text where the embedding is the embedding we just generated. And I'll hand it back to Alan to walk through the next step of the process.
So there's a few tips that you should remember when you're doing your data pre-processing. Number one is that clean data matters. So if you garbage in, garbage out. If you put data it's actually irrelevant data is not that important, not that terrible. It's actually data that's wrong. So if you put in answers that are semantically wrong, your LLM is going to give you actually wrong answers. The second thing is to actually properly split your data. And this is kind of a 200 level type of tip here. So when you're processing a very large document, you don't want to store the entire document into the vector database. What you actually want to do is you want to chunk up the document into pieces that are small enough that you could put in the large language model. And when you chunk it up, you don't chunk it up, let's say take a document and evenly split into 10 chunks. What you would do is that you would take the document and you would split it into 10 overlapping chunks. And this is necessary because the semantic search capability needs to have a little bit for a particular paragraph of text. It only makes sense if it has a little bit of information about the previous paragraph of text. So you have to be very smart, and this is something that you need to, there's no out of the magic answer for every piece of text. You got to be really smart about it. The third thing that you want to do is you want to be careful about loading the information at speed. So one of the nice things about Cassandra is that it can do a lot of parallel inserts at the order of thousands of records per second for just even like a small 3-node cluster. So you want to leverage parallelization. We have some tools called ds-bulk that helps you load the data faster. Now, the other part that we have to be very careful is keeping the data safe, especially if you're trying to leverage your chat history for few-shot learning. You have to make sure you strip out all the PII data. So, customers often do things like put in their tokens in the chat history, things of that sort, their proprietary secrets. You want to make sure that's kept out of your data set. And last but not least, the large language model is only as good as the data it has. So you need to make sure that the information you have is relevant and updated on a regular basis. Okay, with that, let's kind of get into the details of prompt engineering. So the purpose of prompt engineering is to make sure that the prompt that's being sent to the LLM is as contextually relevant as possible. And this is not easy because LLMs are inherently, they're kind of like human beings. There's only a certain amount of working memory that it has. So it has something we'll call the token limit. You can't throw your entire knowledge base into the LLM because there's simply not enough memory for the working memory for the LLM to do so. So we have prompt templates and testing frameworks that you can use, and it's really important to kind of compare all the various prompts. Now, there's a bunch of challenges. So the first challenge is, how do we make sure that the results are qualitatively good? So how do you actually go do around that testing? Sometimes there's a balance of detail. You want to give enough information to the LLM, but you don't want to give too much LLM information to the LLM, otherwise it gives very vague responses. And then last but not least, there's relevancy and safety. So how do we prevent the LLM from saying harmful things, irrelevant things, or very inappropriate things? How do we do all that? So kind of let's go into the data flow. So let's say a customer uses the application, calls the NoSQL assistant with a question. The first thing that happens is that the NoSQL assistant calls the Vertex AI to get the embedding. So what for that question, what are vectors that are close to it? And then this way is just a reminder of how this is done is that there's the database already has all these vectors in it, and the question that's being asked is related to some of those pieces of data, in this case product information, and returns the correct product information. So for example, how do I generate a token? This turns back into the 1,500 float vector, and it finds the closest ones. And so when you're doing the vector, when you're calling the vector store, not only are you calling the vector content, but you're also calling the vector store, the Cassandra database, for information that's relevant about the user. So what is the elements of the good prompt? So a good prompt has the directive. So what kind of bot that person is. It usually has information about the user itself, like who's this particular person, what has that person particularly done in the past, and then also the previous interactions with the user. So this is what we often call the chat history. So when somebody's typing in and having a conversation, just like a regular human being, the LLM needs to know what are the previous chats it had in the past and the context for that. Then also the prompt would have relevant information, like the relevant documents that give the answer. And then finally, of course, the prompt has the user's question. So let's take a look at, this is kind of a subset of all this information, but let's take a look at if the user asked, how do I generate a token? Inside the prompt, it would have a directive. So in this case, we're using the person's profile information, we determine that this is an advanced user trying to perform some actions in the database. And this is very helpful because if you tell the LLM that this is an advanced user, it ends up not providing the user more advanced answers. So like more succinct code and things of that sort. It assumes that the user knows how to use Cassandra already. Now we also provide information about the user and some of the databases that the person has created. These are just regular key value pair lookups in Cassandra, nothing fancy here. And then we have a bunch of unstructured data. In this case, we're showing similar chat history conversations with this user. And you can see over here, there's like 3 different conversations with various folks like Melissa, who's one of our chat support reps, who gives answers on how to connect to a particular API for generating a token. Talk a little bit about prompt selection. So what you would do is that for prompt selection, you would use the information about the user's profile, the recent history, and then select a particular prompt to use. And this prompt is basic template. You would select a prompt template to use. So in this scenario, we have 2 types of prompts. One is a learner prompt template, and the other is a qualified user prompt template. And this is what a qualified user prompt template would look like. It would say, oh, you should answer, okay, sorry, this is a little bit cut off, but say you should answer customer questions. It tells that this person is a qualified user. And then the learner template, what it says that you are giving answers to someone who's new to DataStax and Cassandra. So be especially helpful and be a little bit more verbose on how you answer the questions. And if you look inside the prompt template, it has both a little bit, it has information about, helpful responses from intercom. So this is used for prompt templating, for few shot learning. It has the user information and it has the user's questions. So we're going to give a demo of this. So Alex will show the Astra Assistant, how to construct the prompt templates, and how to test with some of the history. Okay, hand it over to you.
Awesome. So what you're seeing here is just my IDE, PyCharm. And to manage prompts, we use just the LangChain prompt templates. So both of the templates that Alan just mentioned are within a prompts directory. They're both YAML files, and these templates are pretty straightforward. Essentially, we define that this YAML file is a prompt. We define input variables, right? Here, there's only a single input variable, which is the output of the vector search, and that's pretty much about it. The more interesting part is how the prompt template is actually selected. So within kind of our main bot code, we have a very simple, method to get the persona, right? We check the user's information on user, right? When a user registers for a product, we basically ask them a questionnaire on if they've used Cassandra before, what their primary programming language is. And basically based on these responses, we determine if we want to give them the learner template or the qualified template that Alan just mentioned. So here's where we actually select the template, and then you've seen this a couple times now. Here are the actual templates, and we really struggled with kind of how do you actually test these templates? How do you actually make sure that the responses are high quality? So to basically debug this process and consistently improve our templates, we built a pretty cool Slack bot. So let me set that up real quick. Okay, awesome. So on the left, we have just the dashboard of our product and the chatbot. And on the right, we have a Slack channel we set up to automatically log all of the prompts along with the responses, so we can keep reviewing and improving the quality. So I'm just going to ask a simple question to the chatbot. And on the right, we can see the entire prompt along with the response. So I'm just going to scroll up a bit. So here we can see we have the directive. Basically, over here is the full prompt that Alan just talked about. So first we have the directive. We then have the output of the vector search, right? So here we can see a couple pieces of documentation. We have information on the user. So here's the user name, their email, their primary programming language, and we have information on all their databases. What's pretty interesting here is you can feed the LLM raw JSON, and it's able to interpret all that data. And then finally, we have the response that was actually fed back to the user. So really our process of testing and improving the prompt has been reviewing all the prompts, reviewing all the responses. Let's say we get bad documentation bad documentation back. Maybe we'd update the data in the vector store. Let's say maybe there isn't enough information on a topic. We insert new documentation in the vector store. But really, it's just been kind of this iterative process of, we review the prompt and response, and we kind of keep improving. And now I'll hand it back to you.
And just before you go there, actually, you bring up your screen for a second.
Yes.
Go back to there. You can see if you look in the document in the prompt template in the prompt, there's a lot of information in here. And if you go up into the responses, the prompt template, even to the human eye, doesn't look super understandable. So for example, there's this in the middle of the screen that says, the token will no longer exist. The length of time to persist the token is configurable. That's unrelated to how to generate a token. And so one of the things that we notice is that the semantic search that you're doing from the vector store, it's more of a gross level search. It doesn't exactly understand the context of the question. It's able to get things that are related to it. And the LLM is extremely good at ignoring irrelevant information. So if we kind of go back to, I'm going to kind of, so talking a little bit about If you can stop your share screen, I'm going to show you some particular tips that you can use to help improve your prompts. So the first thing is vector search. So what are the things that you really care about the vector search? Number one is that if there's no data that's coming back relevant from your knowledge base, there's a very high probability that you're going to have a hallucination. And the other thing too is that because LLMs are so good at rejecting irrelevant information, it's really a good idea to get as many nearest neighbors as possible, at least whatever would fit within the prompt. And then actually there's another advanced algorithm called maximal marginal relevance, that what it does is that it takes the, let's say, 100 nearest neighbors, and it can isolate it down to the 10 most nearest neighbors that's most relevant for this particular prompt. And the reason why that's very important, and this is a kind of a 200 level type of use case, is that approximate nearest neighbor algorithm, which is the underlying algorithm used for nearest neighbor, is very, very susceptible for duplicate or near duplicate vectors in your prompt. So, for example, if you're scraping your web page, your web pages, and you have 5 web pages with almost identical information, what ends up happening is that it fills up the database with those vectors. And if it so happens that the those duplicates were also irrelevant, what happens is if you search for, let's say, 5 nearest neighbors, then what happens is that all 5 nearest neighbors end up being data becomes irrelevant. Whereas if you use a wider search, let's say 50, and then you ask for 50 nearest neighbors, and then ask for the 5 most different documents within that set of 50, all the duplicates automatically get removed because of this maximal marginal relevance. It basically tries to find out the most distinct pieces of information. So this is kind of an advanced thing that you should remember to use, especially if you're concerned of your system having duplicate data. There's also another bunch of other things that we've learned in prompt engineering. So number one is, because this is a real-time application, you want to respond to the user as quickly as possible. So you want to fetch as much context from your database in parallel. So one of the optimizations that you didn't see underneath the hood is that the data is being fetched in parallel, like calling the vector search for getting the user information, getting the user activity, getting the chat history, and as well as getting the documents that are relevant. That's all happening in parallel against Cassandra, which is great because Cassandra itself is built as a parallelizable database. You got to be very careful about managing the token size. So this is important not just for making sure that it's not just important for speed, but it's also important due to cost. And then you want to have all the tools you need to simplify your development. So prompt templates in particular is a very, very easy way to simplify the development. And in our case, because our company uses Slack so much, if we want to democratize more people testing out these LLMs, we use Slack as a way that our customer support reps can look at all the data that's coming back and forth from that particular bot. And last but not least, you have to, for hallucinations, you really got to kind of test it out and then figure out what's the problem, iterate, and constantly improve improve your prompts to reduce the hallucinations. All right. So with that, the next portion is actually, so we've talked about generating the prompt. Now let's talk about execution of the LLM. And so the way it would happen is that we're going to start from after the prompt is generated. The first thing that we're going to do is that instead of calling the LLM directly, we do actually a cache lookup. So we're calling the vector store to see if that particular question has been asked before. And if it's not in the cache, that's at the time when we actually invoke the LLM. So calling this text bison LLM model and getting the answer. And at that point, after we get the answer, we store the chat history back in the vector store. We also store the cached value into the vector store as well for further use. And then we return the response to the user. So just to give you some context to here, some other lessons learned. When we're doing caching, you got to be really careful about privacy. So especially when you're doing a chat bot, usually people are having one-on-one conversations that are private. And so this doesn't lend itself very well, like our Astra agent, unfortunately, doesn't lend itself very well to caching because usually the conversations are in the context of that particular person. And then to also reduce the hallucinations, there's a lot of settings in the LLM, the temperature, the k-value, p-value, etc., that you can play with in order to generate, to see whether or not the answers are correct. And last but not least, one of the things you need to do before you roll out is you need to capture qualitatively these conversations are good conversations or bad conversations. So what we do is that we actually capture a thumbs up, thumbs down of these conversations are good conversations and bad conversations. And then we use that to understand, we use that as feedback to improve our prompt templates and improve our prompts down the road. One of the other things that we made a lot of usage of is LangChain. So LangChain has these key abstractions for accelerating development of your application. The first key abstraction that we use is a thing called indexes. This is the data like for retrieving the chat history as well as the DB. Retrieving the product documentation. We use the prompt template capability to generate contextually relevant prompts. In fact, we have this feature in Cas.io that you can write the prompt template, and then the prompt template and in the prompt template itself, you can kind of feed in CQL type functions to just auto-populate the prompt template. We use this a algorithm called the maximal marginal relevance. This is kind of an advanced algorithm on top of vector search to improve the relevancy of the data coming back from our database. We leverage the memory abstraction to record all the chat history. And underneath the hood, there's you can leverage something called a semantic memory. So instead of just pulling all, like let's say the last 100 chat interactions, it's able to semantically figure out what are the previous interactions that are relevant to the question the person is using. And then last, we use the cache for improving the performance and the cost. All right, so with that, I recommend you guys to get started. We can do a little demo. Why don't, Alex, can you show exactly how you would provision the vector database?
So if you haven't done so, like Alan said, you can create an Astra account at astra.datastax.com/register. Once you've done that, you'll see the dashboard that looks like this, and you really can create a vector store in just a couple minutes. So you're just going to click this Create Database button at the top of the screen. You're going to select Serverless with Vector, enter some basic details like your database name, your key space name. Finally, choose a region, and a couple minutes later, you will have your vector database in the region you select. So really, we encourage everyone to give this a try. And if you need any additional help, feel free to ask the NoSQL assistant at the bottom of the screen.
All right, so with that, I want to tell you a little bit about what we're going to be doing in the future. So what we've done is that we've connected our chatbot to our internal data warehouse, which is BigQuery. And we're going to leverage Looker, which is a reporting system on top of BigQuery, to generate a lot of reports on how people are doing and using the chatbot. What we also hope to do is that right now the chatbot is integrated into the NoSQL, into the page, but there's no reason why that this is the only location where you can integrate the chatbot. So what we plan to actually do is integrate that into the shell, the CQL shell on the website, or potentially integrate it directly into ChatGPT as a ChatGPT plugin. And then last but not least, we plan to leverage the NoSQL Assistant to also do email follow-ups. So not only can your agent be reactive, you ask it a question, it gives an answer, but you can also use the agent to predict when the person would want to interact with you and generate automatically relevant emails to help that user along their journey. So this is just kind of the beginning. There's a lot of other things that we want to talk about in the next while. So we're going to talk a lot about autonomous AI agents. You may have heard this thing called AutoGPT. So this is the idea of leveraging multiple LLM calls in sequence or in parallel to get to a particular to enable a particular outcome, whether it's fixing your database, things of that sort. So we're going to be experimenting a lot with that and talking about it. We're also going to be talking about advanced retrieval-augmented generation algorithms. So we talked a little bit about the maximal marginal relevance algorithm. Next time around, I really want to get into the details of the math behind it. Why is approximate nearest neighbor and k nearest neighbor algorithm useful, but also what are the limitations? So we want to talk a little bit about the limitations of vector search. And then we're going to talk about things such as the forward-looking augmented retrieval generation algorithm, also known as FLAIR. These are advanced algorithms that instead of doing just one API call to your vector store, getting the content, and then getting content and putting into the LLM and to summarize a response, this is whereby the agent can actually make multiple calls to the vector store and multiple calls to the LLMs to actually summarize and extract information, which is very similar to what us humans do. So for example, if we're reading a book, if we want to get an answer, we would go read different portions of the book, we'd jump around with the book, summarize, go back to the places we forgot about, and then try to come up with the answer by going to iteratively calling, looking at different sections of the book, processing, etc. And then last but not least, we want to talk about what this agent memory is. So the idea behind how do we create a human-like memory for autonomous AI agents. And so we're going to get into the details of how DataStax and the Cassandra community are trying to push this technology forward. So we got a lot of resources that we've put together that you could do more reading. And in terms of next step, we love to see what you build. So if you're going to build something, let's schedule a live end-to-end demonstration. We can demonstrate what we have, and we'd love to see yours. Let's schedule a collaborative workshop. So in the future, what I hope to do is build a community of AI agent builders, and we're going to show each other what we've been building over the last month. And so we want to have a regular touch point with the community to do so. And last but not least, try AstraDB with vector search and build some awesome LLMs and awesome AI agents. Thank you.